Hello. In this video, we're going to cover Understand Routers, which is an objective in the MTA Networking Fundamentals exam. A couple of things that we want to know going into this is first, so some of the definitions is a direct connected route. And so what this is if we have an actual physical connection between two routers. So like two routers connected by a cable, two routers connected by a fiber line, that is going to be a directly connected route. It's always two routers and it's always a direct connection, which is the reason we have that word. Directly connected in the name. This is always going to be the fastest route out of any possible route. We also have a static route. A static route is going to be a specific route configured by a network administrator for special routing circumstances. And what this would be is, say for instance, there's a specific reason why packets should be routed a certain way through the network, rather than letting the computer just decide however it wants to route and using various routers along the way. The administrator is going to specifically say program which routers are supposed to be used for that traffic. Dynamic routing is when we use protocols or rules to update and maintain a routing table, and then that routing table is used to determine which path is best to send that packet of information. Just real quick, one thing that you might need to know is TCP/IP is the default routing protocol for Windows. So if you're using dynamic routing with a Windows device and do not change the routing protocol, the default is TCP/IP. And then a routing table. So a routing table it's basically just a bunch of entries, and these entries have known network paths, and it's going to include things like the next hop. And what that is if you're routing something through that router, that's going to be the next place that it's going to try to send it if it doesn't know where else to go. It's also going to include information, statistics about each of those pathways. And again, depending on the dynamic routing protocol that you're using, each of that information is going to be weighed differently. But basically what this routing table is it's just a list of information of possible paths that your information could take as it's being routed to different destinations. And your computer will use that information to decide which path is best. Something that you might need to know for the test is the routing tables are stored in the RAM of a router. And different protocols use more RAM or less RAM because of how complex they are. Some more definitions is default route. The default route is always 0.0.0.0 in a routing table. This is the route that we use anytime information is supposed to leave the network. And so what's going to happen is the router is going to, if it gets information that is supposed to go to an IP address that is not in its network, it's not going to know where to send it. And so what we're telling it is the default route. If you don't know where to send this, send it to 0.0.0.0. And that's actually going to be used to route the traffic out of our local network using our default gateway. Also, two more definitions that you're going to need to know. We have RIP, and that is Routing Information Protocol. This is what's called a distance vector routing protocol. And basically what it does is it takes a look at the possible paths, and it just counts the number of routers between you and the destination, and it chooses the path based on the smallest number of hops or smallest number of routers that it has to go through. RIP is limited to 15 hops, so it's not really good for large networks. And then we have OSPF, which is Open Shortest Path First. And this is what's called a link state routing protocol. And what this does is it actually looks at statistics and keeps track of statistics based on each of the paths. and it will use an algorithm or a series of steps to determine the shortest path through the network. So the shortest path may actually not be the fewest number of hops, because some of those hops could be faster routers. RIP and OSPF are two of the routing protocols that are specifically listed in the objectives for the test. So these are probably two that we're going to need to know. So first, we're going to take a look at distance vector routing protocol. So this would be our RIP. And so with RIP, what it's going to do is, so if we're going from the left and our destination is on the right, it's going to look at the two paths. You see the path across the top and the path across the bottom. And it's going to count from its router 1, 2, 3 hops across that top path. And then it's going to count 1, 2, 3, 4 hops across that bottom path. And so if you were using the distance vector routing protocol, RIP, your router would choose the top path, because it has fewer hops. Now, as we can see, if we have a linked state routing protocol, things are going to look a little bit different. And so using the same setup, we look across the top, and the line in between each of the routers across the top is only can transmit data at 10 megabits per second. Whereas on the bottom, we have each of these links runs at 100 megabits per second. And so then we see the numbers here. So across the top, that we have 10 megabits per second and then a 100 above it. So that's actually going to be the metric that is going to be assigned to that. And the larger the metric, it's actually better to have a smaller number. And so we see, because this is such a slow link, it's going to have a large number like 100. And then we see on the bottom, because 100 megabits per second is faster, it's going to have a lower number, which indicates a better route. And so we see that if we're using link state routing protocol, even though there's fewer hops across that top one, the metric for that path would be 200, whereas the metric for the bottom path would be 30, because it would be 3 hops, or it'd be 3 or 4 hops, but 3 links. Each one of them at 30. The metric is 30 or 10 for each of them, so 30 altogether. So we can see that the link state routing protocol, this would be our OSPF, or Open Shortest Path First. This would give us a different path to choose. It would actually choose the lower path instead of the top path. Now, one of the disadvantages to something like this over RIP is that the more complex the route is, there's more information that has to be stored in the RAM of the router. And so these more complex routing protocols are going to be a bigger table, and it's going to take up more RAM. As we can see here, RIP is better for small private networks. Again, it can only support up to 15 hops for its routing table, and it's also better for smaller private networks, because in a small private network, we typically aren't going to have a lot of different types of links. We're not going to have a lot of different kinds of cables. We're mostly going to be using the same types of devices. And so there's probably not going to be a significant difference in the speed or other types of metrics on different paths. OSPF is better for larger private networks, because it's going to take into account the fact that there could be different types of wiring, Ethernet cables that offer faster throughput. There could be different types of devices on that. And also the larger network, if we have more than 15 hops, the RIP is not adequate for that. This is a routing table. So I went ahead and just did route print on my computer. And if we look down here, we see an active routes. So that very first one, remember, that's our default route, and that's 0.0.0. And so basically what we're saying is, if you don't know where to send this, you're going to send it out here. And of course, that if we look at the gateway, it's 10.104.4.1, and that is our default gateway. And then we see the metric for that is 25, and so that default that direct route is always going to be better. And then we see here there's just various other destination IP addresses, and these are actually This was propagated because of some of the different ping protocols that I ran recently in preparation for some of the other videos. And so we see here like 10.104.4.1. So that was um, where I was pinging another network asset, and we see that that is on link. And what that means is that that's not going to be leaving our network. And then we see a couple down from that 127.0.0.0 and 127.0.0.1. Remember, those are the local loopback addresses, and so so I'm actually using my network interface card to ping my network interface card, and so that gives us an on-link gateway. And then again, we have our 224, and that's going to be that multicast address, and that's again also on link. And so again, this routing table, this can be updated either by adding static routes. So like if I make a determination that if I can put in a destination IP address, and I can tell this computer that if you're trying to reach this destination IP address, you're always going to use this route. Other than that, what will happen is as if I open a web browser and try to reach a certain IP address, it's going to dynamically create an entry here based on the route that is taken. Next thing that we want to cover is network address translation, or NAT. So NAT translate private addresses to public addresses over a NAT router. This allows you to connect private network to the internet. And if we remember, there's a difference between private IP addresses and public IP addresses. So here we see this is kind of like how the NAT works. So over on the left-hand side, we have our private network. And we see that inside the private network, we have our nodes. They're in the 192.168.1 domain. Remember, this is our Class C private network. And because these are private IP addresses, we cannot route these out to the public internet. Because remember, the whole thing that happened here is we were running out of IP addresses, so they carved out these ranges. And so there's a pretty good chance that there are other computers, even just in in our very close proximity in our city, that have this same IP address. And so if we were to send traffic out on the network with this tagged IP, it would cause confusion. If we look over on the left-hand side of the NAT router, we see 137.65.7.2. So this is actually the public IP address for our network. This would have been assigned by our internet service provider, or ISP. And so what the NAT router is going to do is it's actually going to sit in between our private network and the public network. And as we try to send packets out from our network, it's going to take that private IP address and it's going to translate it to the public IP address and then send it out on the internet. And then if anything comes back into that public IP address, it's going to then translate it back to the private IP address. So that is understanding routers. Hopefully it gives you just a little bit more understanding about how routers work on our networks.